let's say this is A, right? This area here, it's A. So A is the target. What is the probability when Sahil picks a dart and throws it at random to hit this area? Yes.
If you assume an even distribution would be the area of A divided by the area of B.
Right. There's no B yet.
Well, the outside one.
Right. So the probability for, say, dart to hit A, we'll just call that the probability of A, is the area of A, so the size of A, divided by the size of the universe. In my case, the universe is the board or the wall, right? Let's say the wall. Because it's a uniform throw. So throwing darts uniformly. We are assuming here that he's going to hit the wall. Right? The wall is everything the dart can go. Throws one at random. What's the chance of hitting this? It's pretty small, right? Because look at this wall. This wall is big and the target is small. Of course, if you throw darts not at random, you're much more likely to hit that target, right? But if you throw them, close your eyes, throw them completely at random, that's a small area to hit. Now, let's assume I have this, let's say very small. Let's assume I have another thing, another area here. We're going to call B. So B is a different area. Now suppose Sahil closes his eyes, throw a dart at random, and I tell him, you hit B. So this is small, so that's our first experiment. But at the second experiment here, we say throw dart at random. The probability of A is still very small, because the same one like before. The darts flow at random to the board. But now we have event B given, which is we have the information that hit B area. So that's given. Somebody, God, comes and says, you hit B. Or Sahil, you hit B. Now, what is the probability of that hitting A given that it hit B? So clearly hitting B changes the outcome of A, right? Initially, if you didn't know anything about hitting B or not B, the dart could have been here, or here, or here, or here, anywhere in this wall, equally likely. Which means chance to hit A was quite small. This area of A compared to the size of the wall is probably like 1 in 1,000. But now if you say, you hit B, that's not a probability, that's a statement. It's a known information that the dart is in here. So out of the sudden, the realm of possibilities, it's not anymore for darts to be here, or here, or here, or here, so on and so forth, right? That's not possible anymore, because we know that the dart hit B. So what is now the chance, given that it hit B, to have hit A?
The probability of the size of A intersect B over the size of B.
Right. But what is that in here? Like
that would be
in English.
If you filled in just the part of A that's inside of the B circle.
So now we know that that is in B, right? Can it be here?
No.
Here? No. So it has to be in B. Only B is allowed now. This B is a restricted probability space. It's of course part of the universe, it's part of the wall, but it's already given that the dot hit B. So we're not worried about cases outside B because those cases are not possible anymore in this circumstance. And now what is the probability of A hit given B? That is probability of A given B formally, right? Because we know B. B is somebody told us you hit B already. So how do we think of that? Well, out of the space of possibilities, which is now B, all possibilities. So this is hitting A out of all possibilities. But who's hitting A now? Since this is not allowed, this part of A is not possible anymore. Hitting A means now the size of A intersect B. Right? Because again, that side is not possible. So what does it mean to hit A? It means to be in here. This in here is A intersect A. And what are the set of all possibilities now? Given B, size of B. That is uniform. Of course, if probabilities are not uniform, we wouldn't get this formula here. So if it's not uniform, we would get the probability of A and B divided by the probability of B. Now, so from here, we can say, if we multiply, if we read it, P of A given B times the probability of B we could have done the same thinking from the other side. The way we reason in here, and we got P of A given B times probability of B, we could have gotten P of B given A times the probability of A. So the way this implication goes, like this. All I did, how did I get this? Where is this coming from? In these formulas here, what did I do? I simply multiplied this P of B with P of A given B. Right? So I read it as P of A and B, there's this stuff in here, equal with P of A given B times the P of B. So it's a simple multiplication of this. And I can think of this common sense as in A happens, and then B happens given A, or the same event A and B could happen as B happens and A happens given A, or given B. So either way, we obtain the event A and B, which is called a joint of two random variables. This is called a joint. This in here is called a conditional. And we've seen last time an example with a die. We rolled the die. The probability spaces were the possibilities of 1 to 6. And we had two events. One was even and one was at least 3. So we were, if you look at your notes from last time, we have the intersection of the two events, even and at least 3. and the side of, even but not 3, or more than 3 but not even, so on and so forth. One thing I want to point out here is that what is independence? Of random variables. Those are random variables A and B. The definition, we'll come back to this later today. The definition is A does not depend on B. That's the same as saying probability is A does not change by known B. No wing. That's the same as saying as once you know B, it's the same as not knowing B. That's what independence means. Probability of A. When I say A like this, I mean A having a specific value. A is a random variable, so it has possible values. A could be 1 or 2 or 3, or Virgil, or John, or Smith, or something, And when I'm saying the probability of having a certain value is the same whether you know B or not. So then, this here, it's called Bayes' rule, right? This whole equation. I could say, okay, if that's true, then probability of B given A is probability of A given B times probability of B divided by probability of A. How much is this now? If P of A given B is the same as P of A, how much is this fraction? So that means B does not depend on A. So again, this equation I got from here, right? By writing, I was looking to obtain the Base Theorem. I was looking at this equation and I say, I'm only reading the left side and the right side. So I can get P of B given A is that stuff there. P of A given B times probability of B divided by probability of A. That's base. And it gives one conditional as a function of the other. It's useful when I have one conditional, but I need the other one. So P of B given A is not the same as P of A given B. So you need to multiply with the two marginals. Okay? So let's look at some more examples of conditional and Bayes theorem. Family has two kids. The older and younger. Probability of any kid to be a boy is the same as probability of any kid to be a girl. 1/2. So if I compute the probability of having two boys, right? That's the probability of B, boy, boy. It's 1/2 times 1/2, 1/4. I want to ask, what's the probability of a family with two kids? Both kids are boys. That's 1/4. But if I ask probability of two boys, given that the older is a boy, so now I have a context. I already know that the older is a boy. What do I have now? It's not 1/4 anymore. I already know the older one is a boy. So what's what am I looking now for? It's still the event boy divided by, now that the older one is a boy, I have a restricted space. What's my space now if the older is a boy? Yes.
This first boy, the younger boy.
So what are the possibilities if the older is a boy?
Either the younger is a boy or the younger is a girl.
Right, so I have, let's assume we write older, younger sequence. So this is older is a boy and the younger is a boy, or older is a boy and younger is a girl, right? And that is now how much? This probability. It's 1/2, right? Which you could have thought of, since the older one, it's already a boy, I'm not worried about that. There's only coming down to the younger one being either a boy or a girl, which is 50-50. What if I say probability of 2 boys, given that one of them is boy? So I'm not saying the older one is a boy, I'm saying either the older or the younger is a boy. That's a known thing. That's a restricted space. Because I have a conditional, so now I have event BB, that's sizes of. What are the possibilities now? One of them is a boy. Either have boy or
Boy-girl.
I should put it as a set. Boy or boy-girl or
Girl-boy.
girl-boy. So what is this now? 1/3. So the best way to understand conditionals is to ask yourself how the given part restricts my space. Instead of having the whole wall as possibilities, somebody told me, you hit B. That's a given information, that's not a random variable. Somebody just told you what the value of that random variable is. You hit B, so it's not outside B. So now what is my probability space? Is restricted. Same thing in here. This is a restricted space. It's not all possibilities because I've been told the older one is a boy. Same thing in here, another restricted space. I've been told that one of them is a boy. So the first thing you think about conditionals is ask yourself, what does this conditional mean? What is in the space now that I have to deal with? Here's another example. I have a bag of objects with 2 properties, attributes, shape and color. And I have a joint table. So those are 2 random variables. Right? There's many objects, either square or round. So shape is either a square or a round, and the color is either red or blue or green. So one variable is binary, can be either square or round, and the color is red or blue or green, one of those 3 options. So here how the joint table looks like. That's given the probability of SC. How many options I have for SC as a joint? An object can be one of how many possibilities? 6. So this is 6 possibilities. Here's the square. Say red, blue, green, square. Here's the round. And those are the probabilities. So this is 0.25, 0.10, 0.21, 0.17, 0.04, 0.23. Those values should sum to 1. Because this now is a random variable, SC is a joint random variable. A joint random variable, SC, has 6 possibilities. Those are the possibilities of what object could look like, right? It's either square round, or square blue, or square green, or round red, or round blue, or round green. There's 6 possibilities. They have to sum up to 1, because every object has to be one of those 6 things. In this context, what is the probability? So first of all, let's write down here. This here is the probability what? How can I write this value 0.25? It's the square and red, right? This here is the probability of round and green. That's informal for saying probability of the shape is round and the color is green. What this informally means, round green, it's saying the probability for shape being round. Let's write that in words. Shape is round and color is green. That's what it means. And you can read any one of those 6 values the same way. What is this? Probability of shape being round and color being blue. Now what is conditionals? What is the probability of, say, sometimes, because I'm not consistent, I put square brackets, sometimes round brackets, sorry about that. I think you should put square brackets everywhere, but if you put round brackets, we won't mind, we'll understand what you write. Many books use round brackets and some other use square brackets. I'll try to put round. Probability of, what is probability of red given the shape? So, how do we read this in English? This is the probability of color being red given that shape is square. So that's the same as saying probability of color being red given shape is square. So what is given means shape equals square. It's a restricted space, right? So it's restricting to what? When I say shape equals square in the given side, is restricted to?
The row that square corresponds with on the table.
Very good. So this is restricted. This whole thing here, restricted to first row. Right? This is the restricted row here. Right? Because somebody sets a square, out of a sudden this row is not possible. It's a square. So now, what is the probability of red in that square? In that row, that is square. So how much is it? How do I do that? What is the value? Somebody else. Yes. 0.25. 0.25, that's the value in here, right? Divided by?
All the sum of
0.25 plus 0.10 plus 0.21, which is the probability of being red and square, divided by what is the sum of those three things? Probability of square. just being a square in general. Right? How many people follow me? Hands up. Okay. I would like to actually write that down. So I know you guys can't erase that easily. Sorry about that. What is the probability of red or square? I can write it right here. Probability of square is the sum on this row, right? Is the 0.25 plus 0.10 plus 0.21. And I have a value for that, 56. And I can compute probability of a round, which is 0.17 plus 0.04 plus 0.23. That gives me 0.44. I'm summing up those three things. This is squares can be here, 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 the sum, that's all the squares. Rounds can be here or here, here, that's the sum of all rounds. Are we surprised that those two things sum to 1? No, because the whole thing sums to 1, and this 0.56 is the sum of those three, 0.44 is the sum of those three, right? And now I obtain the distribution of shape, right? This in here is the distribution of random variable S, shape. So if you just look at shapes, you ignore the colors for a moment. You look at the bag of objects, and you say, I ignore the colors. Red, blue, or green don't matter to me. Only thing that matters is the shape. What is the probability of being a square versus a round? 56 versus 44. So let's make this a little bit better square. This process is called marginalization. Of joint or random variable S. So what I did, I took the whole joint, the table of 6 things, and I say I want to marginalize to obtain only probabilities for the shape, ignoring the colors. I could do the same to obtain the probabilities for the color, right? Try to put them here. Suppose I want to marginalize this to obtain the probabilities. I'm going to sum it up. What do I have for the colors? If I say ignore the shapes, I don't care about shapes, square or round. I only care about reds versus blues versus green. So what do I get? 0.42, right? This plus this. This is 0.14, and this is 0.44. This is the marginal probabilities. So this is probability of reds here. What I've got is probability of red, probability of blue, and probability of green via marginalization or marginal of joint for random variable C, color. So if I'm to look at my bag and say ignore the shape, just look at the colors, I have 4.42% probability to get reds, 14% chance to get blues, and 44 chance to get out of 100 to get greens. So formally, what we have here is about this marginalization. What we actually said here, the way we got this 0.42, we said probability of red, that's a formal marginalization process, is we apply here a partition rule to say that's the probability of either red or square, let's say red square, plus probability of red and round. Is this the correct partition rule? That you say, if you want a red object, it's either red and square or red and round? Right? Is there any other option for red objects? No. Do I count anything twice? No. So now, I could say, that's how I got 0.42. I added up those two values, right? This was red and square, and this here was probability of round and red. But now if I apply Bayes rule, I get probability of red given square times the probability of square, that's this one, plus red given round times the probability of round. This guy here is that, and this red and round is that. So in general, when we talk about marginals, we can write that probability of x, one of them, is the sum over all possible values of y, of probability of x given y times probability of y. So that's saying if you want red objects, you split these red objects into all the choices for the other variable, that is the shape. And now you get probability of squares and rounds, and then the probability of reds given that choice. So this is a marginal formula. Okay. So we said here we've got probability of, let me write that again, probability of red given squares. We say that's 0.25 divided by squares which are 0.56. Right? That was the probability of red and square times the probability of square, or we can write that as probability of red and square, and now it squares are all three things. So that is the probability of red and square plus the probability of blue and square plus the probability of green and square. That's how we obtain the 0.56 is probability of squares. And then the other way, probability of square given red, it's 0.25, that's the same, it's the probability of both of them. Divide by now what? 0.42, right? Which is the probability of red and square, just before, but this is probability of reds here, and this is probability of red square divided by probability of red square plus the probability of red round. Red square, red round, that's 42, which gives me the probability of reds. The last observation, so critical observation, this is not the same as that. That's a Base theorem. So the Base theorem in this case would say, how does those two depend on each other? Probability of red given square is probability of square given round, given red, times the probability of red divided by probability of the square. So we could verify this, that the ratio between these is exactly the probability of reds versus squares. One more thing I want to point out here, and that is that red conditionals obviously change, let's say color conditionals, change with the premise that is given something. So the probability of, say, color given squares, what is stable? R, D, G. So R given squares is 0.25 divided by 0.56. This is 0.25 divided by 0.56, and this is, no, it's 0.10. And this is 0.21 divided by 0.56. But if I want to do the same probability of color given rounds, now I've got 0.25 divided by 0.44, 0.10 divided by 0.44, and 0.21 divided by 0.44. Sorry, I wrote it wrong. So probability of reds given round, 0.17. 0.04, 0.23. So if you want to look at the distribution of colors among squares, right? This is color among squares. This is color among rounds. This is not the same probability distribution. If you look like color, like the distribution of colors in this row and distribution of colors in the second row, they're not the same, which tells you immediately those variables are dependent. If they be independent, they'll be the same probability no matter what the shape is, but it's not. So they are dependent variables. So one way we can look at dependency is the probability of red equal with the probability of red given the shape? The answer is no. So they are dependent. Another way to look at this, which we're going to prove later today, is to ask, is the probability of red and square, is the probability of red times probability of square? What does that mean? Where is probability of red and square? In the table. It's right here. Where is probability of red?
0.42.
Right here. And where is probability of square?
0.56.
If the product of the marginals, 0.42 and 0.56, would be this value for all values in the table, meaning if 0.10 will be 0.14 times 0.46, and 0.21 will be 0.56 times 0.44, and so on and so forth. If every single cell in the table would be the product of the row probability times the column probability, the marginals, then they will be independent. The answer is no. So, dependent. So, in general, independence, it's equivalent to probability of xy, it's probability of x times probability of y, which means any joint cell has to be the product of marginals. Those are marginals. These are the marginal probability of the colors. These are the marginal of the shape. If every single cell in this table is the product of row times the column, that gives you independent random variables. But those in this example are not independent. If you do all these products, you don't get the values in the table. Okay, so that's what I have to say about this example. Let's do another one. So, erase this maybe. It's another use of conditionals. You guys remember last year the Zika virus in Florida? 2016, South Florida. Zika infection. So we have two random variables. So the population of Florida, that's a universe. Is the population of Florida. That's like 10 million, right? 10 to the 7. H is a random variable. It's called hypothesis. That means has Zika infected. So it has two possibilities, this H. It's either positive, or yes, and negative. No. Another random variable is E, which we call evidence, which is from a blood test. Blood test. Also positive or negative. Now they're not perfect. So probability of positive test given Zika infection is 99%. That's 0.99. That is the probability in terms of random variable. How do I write this? Who's this? Positive test versus Zika infection. So I'm going to say this is H, this is H bar, this is E, and this is E bar. The E bar means negative, E means E positive, H bar means so how do I write positive test given Zika infection in terms of my random variable? Yes.
E given H.
E given H. How about the probability of a positive test given not Zika infected? Say that is 0.01. What is this? Positive test, yes.
E given H bar?
Or not H. Now, that sounds like a reasonable thing, right? I mean, this test is not a bad test. No test is perfect. You should know that. Every blood test or medical test can have a failure mode. This is saying if people have a Zika infection, 99% of the time, this test is going to test positive. And if people don't have a Zika infection, 99% of the time, so this is not the complement of that, right? The complement of this equation is to say what? Given not Zika, probability of a negative test has to be what? These are complement to each other, right? Given not Zika, that's my restricted space right now. I can either have a positive test or a negative test. This has to be 1 minus probability of positive test given not Zika. So that is 1 minus 0.01, that's 0.99. Who's this in terms of my random variables? Not E given, not H. So this is a reasonable test, right? If not Zika, 99% of the time, I'm going to get a negative test. If Zika, 99% of the time, I'm going to get a positive test. So what do we actually want here? In practice, what is the conditional probabilities that we want? We can get the evidence, right? We can easily get everybody in South Florida to make a test. That's easy. So what we really truly want here is to compute what? Probability of, since we can get the evidence for everybody, we can get everybody to the testing line. What do we want to know then? Yes?
Probability of Zika infection given a positive test?
Right. We want probability of Zika given positive test, which in terms of my random variables is H given E. Right? That's what we want, not the other way. So what we can get easily is E given H and E given not H. Those we know this from a table, but this is not the ones we want to measure how spread the outcome is, the Zika. So how do we get this computation done? We apply Base Theorem, right? This is probability of E given H times probability of H divided by probability of E. Let's say we know probability of H in general. This is probability of infection. It's called in medical terms prevalence of Zika. Let's say that is 1 in 100,000. That's 10 to the minus 5. So this is like a prior to say on a Zika infection, look at the Florida population. So that means what? If I have a population of 10 million and the chance of infection is 1 in 100,000, how many people I expect to be infected?
100.
Expected Zika infection. If it's 1 in 100,000 and my population is 10 million, roughly how many cases of Zika I have?
100.
100, right? So that is this P of H times the population. That's 10 to the minus 5 times 10 to the 7. That is roughly, I expect 100 infections, which is realistic, right? When people do this kind of thing, they've seen maybe 100 cases, right? When they start thinking about what is the usefulness of using that test. So then, what do I have here? How do I do this? Probability of E given H is 0.99. Probability of H is 10 to the minus 5 divided now. Now, who is this P of E? We do this via marginalization. So E is two things. It's E given H and E given not H, right? So that is 0.99 times 10 to the 5th minus 5 plus it's actually this is 0.01 times 1 minus. So let's figure out how this, where this formula comes from. Let me write it again. 0.01 times 1 minus 10 to the minus 5. So what is this? This is probability of E given H times probability of H divided by, this is probability of E given H times probability of H plus probability of E given not H times probability of not H. That's how we obtain marginals. P of E is either E given H times probability of H, like one of these formulas, or it's probability of E given not H times probability of not H. So E given H is 0.99, P of H is 10 to the 5th. E given H bar is 0.01, and probability of H bar is 1 minus probability of H. This thing in here is 1 minus probability of H. That's where I got 1 minus 10 to the minus 5. So now if I do calculations, I get 0.000099 divided by 0.000099 plus 0.0099999, which is approximately 0.00099, which is approximately 1 in 1,000. Let's put some red exclamation marks in there. What does 1 in 1,000 mean, really? What did we do? You have a question?
No, not that.
So what does 1 in 1,000 mean? It means if somebody tests positively for Zika, it's actually not that good of an indication people have Zika, right? What we just computed says supposed to get a positive test. If you get a positive test, how likely you are to actually have Zika? Only 1 in 1,000. Okay? So you got to think about that for a second, how this evidence and the hypothesis work together here. The biggest problem was the large population of Florida, 10 million, and the very unlikeliness of people having Zika to start with. You can call this a prior. That is, because of these big numbers, 10 to the 7 and 1 over 10 to the 5th, when I do the calculation, if I get a positive test, it's not a strong indication at all that I have Zika. Now, if I get a negative test, I'm 10,000 times less likely to have Zika, right? So this test is saying that if you test positively, you are so many times more likely to have Zika than if you test negatively. That is true. But even if I test positively, the chances of having Zika is pretty small. Okay? This is something that we need to take home and think about it more. Okay, questions? So what actually happened, this is Florida, 10 million. This is Zika. Right? This is H. Zika. It's very small. The chance of getting Zika, this P of H is 1 divided by 10 to the 5th. So what's up with my test? My test, if you have Zika, you're very likely to get the test. So here's my test. What is this saying, E of H, 99%? What is that E of H computing in here? So this big circle, let me drive it in colors. Let's try this. This is small one. Zika. And this is evidence. What is this E given H? .99. What is this .99 what's the meaning of this .99? E given H. Yes.
99% of the people who have Zika are tested positive for it.
So this is describing the ratios of the green circle, right? It says having Zika, you are in the green circle now. Right? So the premise in here, this H is green. Right? The premise is I'm in the green circle. And now out of the people in the green circle, a large proportion of them has the test positive. That's what it's saying. It's dividing this area here, the intersection by what? This divides the intersection area by what? Yes.
All of H.
All of H, which is the green circle.
Yeah.
That's why it's 99%. But looking the other way, if I get a positive blood test, I could be anywhere in the blue circle. How likely is that I'm Zika? Not that likely. The intersection divided by the E-test is not that big. So if somebody gets evidence blood test, it's not at all clear that they have Zika. That's why we got a probability of only 1 in 1,000. All right? Last example for conditional probabilities. You guys know the Monty Hall problem? That's a typical puzzle offered in high school. So Monty Hall. There are 3 doors, A, B, C, one with a price. Player chooses a door. Say A. Now, Monty Hall opens another door, a different door. Monty Hall, of course, knows what the price is. Without, that has no price, for sure. Let's say as Monty Hall knows. So here are the doors. A, it's locked. That's the door player chooses. Here's the door B, that's open, but no price. And here's the door C, which is still locked. Now the player can stick with A, with the initial choice, with door A, or switch to B. Which is better? So, you're the player, you choose a door. You know there is exactly one price. God, aka Monty Hall, comes and say, I'm going to open one of the other 2 doors that I know for sure has no price in it. And that's always possible, right? Whether you pick a door with a price or not, out of the other two doors is certainly one without the price. So it chooses one, opens, of course there's no price. Now you as a player can choose to stick with your original option or choose the other door that's still locked. What do you do?
Should say C.
Switch to C. Should we switch or should we stay or is the same? Switch. So the probability of A winning given B open, it's still 1/3. That's the probability, original probability. That's the same as original probability of winning, right? If you pick a door at random out of 3 doors, it's 1/3. But what's the probability of C win now that B is open? 2/3. So you should compute those things because you can do it given uniformity and the fact that Monty Halls doesn't open a door at random. If you pick a one without the price will be in those two. Monty Hall doesn't pick one at random. It picks the one with no price. That's where the probability increase comes because the door gets open, it's for sure one without the price. So you should compute those probabilities and see that indeed they're 1/3 and 2/3. So as a player in this problem, you're better off switching. The last thing I want to talk about probabilities, conditional probabilities here. Is linearity of expectation. How do we prove that? Expectation linearity. That is expectation of x plus y. What do we have there? A and B. Let's say A and B. Because it's on the board already. Is the sum over all possible A, B values of A plus B times the probability of A and B. So those are now are numeric variables. A, B, numeric random variables. So now what I can do with this is to say that is the probability for all A values of A times probability of A times probability of B given A plus the probabilities of all AB values of B times probability of B times probability of B given A. What happened here, A plus B got distributed into A and B, two sums. And who's this? This is exactly P of AB, right? By Bayes formula. And this is P of AB. So this product stands for P of AB. I distributed A plus B into a sum with A and a sum with B's. So now what is this? A sum over a bunch of values is the sum of all B's over the sum of all A's values. A P of A times probability of A first. Sorry. B given A plus the sum of all AB values So what I wrote here is instead of summing over all possible values, which are pairs, I split it into two sums, which is sum of sums, over first iterate over values of A, and then iterate over values of B. Overall, I get all pairs in here. And the same thing in here. Instead of saying all pairs, I say sum over all values of B's, of sum over all values of A's. Overall, this term is over all pairs.
Shouldn't in the second line it be probability? It's sum of B times probability of A given B, not B given A.
Right, because the term is the same as before.
Right, but in the second term.
This?
No, right.
Like the second sum.
To the right.
Second signal.
There.
That's the probability of A given B, I think.
Where is it?
But there's.
Yeah. So this is a trick with a lot of summation, both in combinatorics and probabilities as in sets, and then what's coming in induction. You have a set sum over a bunch of values. You can say write that sum as first iterative of all values of B, and then inside each value of B, iterate for each values of A to get all pairs. Or first iterate over all values of A, and then inside that, once you fix a value of A, iterate over all values of B. You still get all pairs. So now, for all this part, I get sum of A. This is a common factor because for values of B, A times P of A doesn't matter, right? So it's A times P of A, common factor, times the sum of over B's, or probability of B given A. So this is a big sum here. Plus sum over all B's, sum over, this is a common factor, B, probability of B, times the sum of probability of A given B. So again, what happened here is B times probability of B does not depend on the value of A. So I can take that as a common factor in front of the sum. In here, A times probability of A does not depend on the value of B, so I take it in front of the sum as a common factor, and then the sum of B distributes over the remaining terms. Who follows me? Okay, this is 1. Because given a particular value of A, I'm back to now all the possibility of B's given that value of A, right? This is given the shape being squared. What are the probabilities for the colors, red, blue, and green? You sum up those probabilities, you get 1. And this is also 1. So this is sum over A of A times probability of A, plus sum over B's of B times probability of B. That's, of course, the expected value of A plus expected value of B. That's by definition. So expected of a sum is the sum of the two expectations, independent of whether these variables are independent or not. You see, I never use the fact that they are independent somehow. This works for any A and B random variables. A little further into this track, if A, B are independent, that means probability of AB is probability of A times probability of B. That's for any AB. I don't need any condition for this linearity to happen. But now I'm in a particular case. In that particular case, I want to compute expected value of A times B. That is the sum over all possibilities for the pair A, B times the probability of A and B. So A value, they're still numerical, but they are independent now. So they satisfy this condition. The joint cell, it's always the product of the two marginals. Well, this is then sum over AB values, A times B times probability of A times probability of B. This is because of independence. Now I've used the independence. I say probability of a joint is the product of A times B. So I do the same trick here. Sum over A, sum of the B, A times B of P of A times P of B, right? This is the same exact thing, but instead of counting over all possible values, I say count over all possible values of A, and for a given value of A, count over all possible values of B, the same term. So it's the same trick I use in here with those two sums. Breaking a sum of pairs into a sum for the first variable times the sum for the second variable. Now what I notice is that A and P of A are independent of B, right? So I could write that as sum over values of A, A times P of A, sum over values of B times P of B. So that's how I get expected of A. This is something that we don't have time to maybe discuss it in class with examples, but it's something that you should take home and say, okay, how does this happen from this step to this step? If A is a bunch of shapes and B is a bunch of colors from my objects, who is this in that context and who is that? Assuming they are independent. Yes?
This is only true when they're independent.
Independent, yes. Because I use, this is where independence come into play. When I say P of AB is P of A times P of B. Here's an exercise for you guys, which is kind of the same calculation. If A, B are independent, that is P of AB is P of A times P of B, then show that the variance of A plus B is the variance of A plus variance of B. That's something that goes pretty much the same way. The variance summation sums just like the expectation, but only if they're independent. The expected distributes over the sum all the time. Variance distributes over the sum, like the expectation distributes over the product, only if they are independent. So you can use the following trick here. Variance of x, the formula was E of x minus E of x squared, which I can write as E of x squared plus E of x squared minus 2x E of x. Right? I just expanded this A minus B squared. That's what I did here. Now expected distributes over So to prove this formula, you're going to need first to walk through this, to write variance as a nicer way. Instead of write the variance as expected of distance to the mean square, do some manipulations first to get it into expected of a square of the random variable minus expected the mean square. And it's a calculation that works for any random variable. Now, with this formula of variance, you plug it in here. And you still have to use the independence because this is true only if they are independent. With this, you get to prove this exercise. So now we've done the independence. This is true for any random variable. If they're independent, the expectation product distributes and the variance sum also distributes. I have for the remaining lecture today and maybe a few minutes next time, a particular case of random variables, a particular conditional situation, which has a name and a modeling practice. That's in your homework. So, Markov chains. You can think of them as simple graphical models. In Markov chains, there are a set of random variables called states. And a time in integers goes to infinity. This is the natural set. And a population of agents that at time t can be exactly in one state. So here's an example. The agents are Massachusetts people going to dinner. The states are Bertucci's, Margaritas, and Sato. There's 3 restaurants. So I have here Bertucci, Margherita, and now the reason this is a simple graphical model is because there is a property. The probability of an agent in a state at time t plus 1 depends only of the previous state for that agent. Previous state means a time t. That is the Markov property. It's also called memoryless. Right? What would that mean for my 3 restaurants here? That property. If I go, the decision I make, I'm an agent, right? I live in Massachusetts, I go to dinner, right? My decision where to go tomorrow's time t plus 1, at one of these restaurants, depends only on what?
Where you were before.
Where I've been today, not before in general, just the last time.
Yeah, the last one.
Right? So depends on time t, but not on times t minus 1, t minus 2, so on and so forth. So for my example, everything that determines when I'm gonna go to a restaurant tomorrow, only depends on today. It doesn't depend on where I've been yesterday or how much I like Bertucci's before or nothing like that, just today. So those are fixed probabilities with fixed transition probabilities from time t to time t plus 1. So here's this example. Staying at Bertucci, like if I go to Bertucci, what's the chance of tomorrow going to Bertucci? That's 0.7. If I go today to Bertucci, what's the chance of tomorrow going to Margarita's? That's 0.2. And what's the chance of going to S? Now you should be able to tell me what's the chance of going to S, because if today I go to Bertucci, what's the chance of tomorrow going to Bertucci, tomorrow going to Margarita, or tomorrow going to S? Those things have to sum to 1, right? Because I have to go somewhere to eat. So what's the chance of going to S? 0.1. Now, those are the transition probabilities. So we call this matrix P, transition probabilities, matrix, transition matrix. So what we're gonna write? Bertucci, we're gonna say Pij, probability of going to J at J, given that previously was in I. So we have Bertucci Margarita, Bertucci Margarita. So I just said that from Bertucci, I read it from a line. So from Bertucci to go at Bertucci 0.7, go at Margarita 0.2, go to Sato 0.1. That is Ij, I is the row, J is the column. That is, if I've been in B, Bertucci, what is the chance of moving to B, M, and S the next day? The important memoryless property is that that decision tomorrow, it's only based on where I'm today. Doesn't matter the history, how I got here. That's actually how a lot of games are programmed, whether it's StarCraft or whether it's chess. They evaluate the current situation. They don't care about how did I get to this current situation in chess or in StarCraft. They say, given the situation right now, what do I do next? So that's called a memoryless experience. I don't count what happened before that situation or before that, just the current situation. So Markov chains, if you can represent a game with states, then you evaluate the current state and you decide what to do from the current state, no matter how you came to that state. That's memoryless. So let's put something on Margaritas now. Margaritas have a retaining state of 0.6. That is, if I go to Margarita, the chance is to go tomorrow again. To Bertucci, 0.3. And to Sato, 0.1. And from Sato, the retention rate is 0.5 to stay there. To move to Bertucci is 0.3. And to move to Margarita is 0.2. So let's write them down in my transition matrix. From Margarita to Bertucci, next day 0.3. Staying in Margarita 0.5, moving to Sato 0.1. From Sato to Bertucci 0.3, staying in Sato 0.5. That's a 0.2.
That doesn't add up to 1.
The middle one, it's 0.6.
Okay? So from, what did we say? From M?
From M to M.
0.6.
6, is that good?
Yeah.
Okay? So the way I read this matrix is what's the probability that this in here is the probability of going to Bertucci next, given that I am in M. Of course, that's not how restaurants work. the chance where I decide to go tomorrow is not only based on what I've been today. But what I've been today has a large impact, right? If you go somewhere you like it a lot, maybe you go next day again. If you don't like it at all, maybe you go somewhere else. But history matters. You don't make those decisions purely on where you eat last time. But games are programmed a lot this way. So here's what happens next. I have here what I have here is the states, Bertucci, Margherita, and Sado. And I have pi at time t, the distribution of agents over states. So initially, pi 0 is initial distribution. Let's say this is 1/3, 1/3, 1/3. Now you can think of this either as a probability, that is to say, Virgil, what's your chance if you just move to Massachusetts, right? This is day 0. What's your chance to picking one of these 3 restaurants? You don't know anything about it? 1/3, 1/3, 1/3, right? I just came in first day eating out in Massachusetts. Or, if you don't like the probability, you can think of it out of 12 million people in Massachusetts. How many of them in the first day go to Bertucci's, Margherita, or Sato? Think of it as a count, because it's the same thing. You can think as a count, how many of the total population goes to there, there, there. Or you can think of, no, if you are one person, you just came in, what's your probability to eating first at one of these restaurants? It's the same exact thing, whatever it's easier. I found it easier to think with counts. I think of 12 million agents, and I think how many of them first day go to Bertucci? 4 million, Margherita, 4 million, Sato, 4 million. What happens that's the transition mechanism. This is day 1. So, how many people would go to these restaurants, assuming this holds? Assuming the transition is correct. How can I tell who's going to Bertucci's day 1? How many people are going to go to Bertucci's? After, not the first day. Initially, it's 1/3, 1/3, 1/3. Let's write it down and see how deep the line has to go. Well, who's coming to Bertucci the next day? Either people that were before at Bertucci, or people who were before at Margherita's, or people who were before at, right. So 1/3 of these people that were in Bertucci the previous day, how many of them will still go to Bertucci? 0.7 times 0.7. Plus 1/3 of the people going to Margherita's times how many of them now from Margherita's will move to Bertucci's?
0.3.
Plus 1/3 of the people that went into Sato times what percentage of them will move to Bertucci? 0.3. How about in here? 1/3, that's the Bertucci people. How many of Bertucci people the previous day will now come to Margherita's? 0.2. 1/3 times, this is Margherita retaining rate, 0.6, right? And this is 1/3 times people from Sato, 0.2. So how much is this stuff? I have it here computed at 433. This is 0.333. And in here, 1/3 of these people. So now I'm in Sato. That's the Bertucci people. How many of the Bertucci people will go to Sato the next day? 0.1 plus. This is the Margherita people. How many of them will go to Sato the next day? Plus this is the Sato people. How many of them will go to Sato retention rate? 0.5, right? I have this computed as 0.233. Now what do we do observe? The probability is not uniform anymore. Because people who went to Bertucci like it a lot, they likely to stay. But the other restaurants are pushing more people to Bertucci than the retention rate is not that great. So then the next day, more people will go to Bertucci. See now, this is still a density distribution. The sum of those three should sum to 1. But there's more to Bertucci because there's effect of the previous day, people liking Bertucci.
Does that mean that after a while you get almost 70% of the population of Bertucci?
Not 70%, but something fixed. It's converging. So what happens the next day? That's day 2. How many people gonna go to Bertucci now? What are the ratio now the previous day in Bertucci? 0.433. How many people of those from previous days will stay? 0.7. Plus, how many people on previous day in Margherita? Times? From Margherita to Bertucci,
0.3.
right? Plus 0.233 times 0.3. That will give me even higher now, 0.473. How about in here? Get 0.433 times 0.2 plus 0.333 times 0.6 plus 0.233 times 0.2, and now I've got here 0.333. This seems to be stable. And in here I got 0.333, that's Bertucci's people times how much? 0.1, right? The transition is the same every day. What changes is the distribution. 0.333 times 0.1 plus 0.233 times 0.5. I get here 0.193. So now, the second day, the distribution is even more skewed. It's more people in Bertucci, Margherita has the same rate, and Sato is going down. The general formula here, if I'm to write this as a general formula, the probability at time t plus 1 to go to Bertucci is what? Can I write that as a general formula? Is how many people been at previous time in Bertucci, right? That's the percent. Who's this? This is 0.433. Times the retention rate is what? Let's say probability of Bertucci going to Bertucci. That's from the table there. Plus, who else goes to Bertucci? Probability a previous round people who were in Margherita times. What's the chance of moving from Margherita to Bertucci? Probability to move to Bertucci once I've been to Margheritas before. That's a fixed probability from this table. From Margherita to Bertucci, 0.3. Plus, what's the chance of moving from Sato? Right? So this, how is this computed? It's saying how many people were before in Bertucci times retention rate. How many people were before in Margherita times probability of moving from Margherita to Bertucci times plus how many people were in Sato times the probability of moving from Sato to Bertucci. So this is eventually convergent. I need one more minute here, 60 seconds. So this equation in matrix form, same exact equation, I can write it as P as a vector at round t plus 1 is just P at round t times the transition matrix. So this is distribution at round t plus 1, distribution at round t, this is transition matrix. It turns out after a few rounds, pi becomes convergence. Often, not always, there's some mathematical properties. So how can I find this pi that's the convergent pi? That convergence is called stationary distribution. Well, obviously one way is to keep iterating this, right? If I keep doing those calculations 100,000 times, I'm going to notice when this becomes convergent, right? Yes?
You can make a system.
Right. So option 1 is to keep iterating till no change. And what's the option 2? The option 2 is to solve for the stationary. That is, solve the equation pi equal pi times p. Because if stationary is convergent, pi t plus 1 is the same as pi t, right? Convergence means it doesn't change anymore. Right? That's what convergence means. Once I apply the transition matrix, I get the same as before. So that is solving that pi is pi times p. Of course, we also know that the sum of pi has to be 1. If you solve this system of equations, you get the stationary distribution. The stationary distribution is what it's the overall rate of people going after a while to Bertucci, Margherita, and Sado. So if that's 0.69, that means overall 69% of the people will go to Margherita. That is the general approach to Markov chains. We're going to talk a little bit more on them on Friday. It should be enough for the homework.
Got a shirt just for discrete.
Very good. Can we press the red button on the camera on the right side?
Virgil,
Yeah.